All right, line A6, learning task 6, we're going to talk about operational amplifier circuits and common ways that we are going to go and use them. We started out by talking just about what an op-amp is, that it's going to be something that is going to be able to take in small amounts of voltage, and then it's going to be able to switch them out to much larger amounts of voltage on our output. Now we're going to start talking about how we use them inside of circuits to go and do more than just a discrete switching. What we looked at in the previous learning task, we were looking at doing discrete switching, one of two states, high or low, or completely positive or completely negative, where we were doing things like we were squaring up a sine wave or stuff like that to go and use the full open loop gain to go and drive that thing all the way in. What we're going to do now is we're going to start to go and attenuate that gain. And the reason that we're going to attenuate the gain is so that we can actually go and get representations of whatever we have on our incoming side of these. That is then going to go and carry through, here's my incoming side, to my outgoing side like that. We want to be able to see what how that carries through from one side over to the other. The first thing we're going to do is we're just going to talk about how we have described the op-amp here before. A couple of things that we need to go and put into place. First of all, let me just erase these over here. First of all, the op-amp does not take in the power through here and then amplify that power out through there. What it does is we've talked about this before, we've got that tiny little voltmeter with an ELF inside of there. The ELF reads the voltmeter, and then the ELF goes and switches to whatever my values of voltage themselves are going to go and be. I'm going to go and have the option of either having a incoming positive or negative, or it might be positive or ground. And inside of here, we're just going to go and switch over from one side over to the other, either to the positive or either to the negative, based on what this voltage over here is going to be. So the drawing as is fairly incomplete because it doesn't show us where we are getting our power from. Ultimately, all of the power that we will deliver out is going to be coming either through here or it is going to be coming through here, depending on whether we are going into the positive section or whether we are going to the negative section. None of the power that is going to be on our output is going to come in through the front end, through the input end over here. And that's really handy for us because there's a lot of cases where we have got small and weak signals that are coming in. A prime example of something like that would be an RTD. If you're not familiar with RTDs, something that as you get further on into more of the industrial, the automation end, you're going to see more of. And it's called a resistive temperature device. Really what it is it is going to be something that is going to be a positive value of voltage that we will attach. It's going to be DC usually. And then that DC is going to go through a resistance. And that resistance type of material is going to go and have a voltage drop on it. Now inside of here, there is paths all the way through to my negative or to my ground. So what I'm going to do right now is I'm just going to leave those paths open for the time being. We're going to refer to them in a second. But we're going to go and refer to this RTD. These RTDs are designed to go and carry tiny, tiny amounts of amperage, milliamps, or in some cases, microamps that are designed to go through them. That's it for the maximum that we can go and pull through, because if we pull more current through them, they do have what we refer to as a PTC, a positive temperature coefficient, which means that as they heat up, so as heat goes up, then the resistance would go up. And this is what we are using them for, is we're using them very often as being our temperature sensors. We've got a lot of processes where we have to monitor temperature. So what we want to do is we want to have a fixed amount of current that is going to go through it. That fixed amount of current that goes through there is then going to be delivered out to this. Now inside of here, there is going to be, remember we said it's like a voltmeter, which means it's got an extremely high impedance. We're going to place our impedance in here into the range of 200,000. 200k ohms, let's say, that we have got for our internal impedance inside of there. That internal impedance inside of there does reference through to my voltage positive and my voltage ground. You can go back to that drawing that we saw in the previous learning task. Once again, not going to be important for us other than to look at this thing as being a 200,000 ohm resistance, and then that this over here is going to be a very small value of resistance. It could be anywhere from 100 to, let's go from 10 to 500 ohms that we are going to go and have through there. We are going to go and have the bulk of our voltage that's going to be dropped across here, but this thing, as the temperature, as the heat around it changes, we are going to go and change our resistance. So if we increase heat, our resistance goes up. If our resistance goes up, the volts that I'm going to go and drop across, if V is equal to I times R, the amount of volts that I'm going to go and drop across it are also going to go up. Because my resistance went up, my volts are going to have gone up. The voltage drop across here, and if the voltage drop has increased up there, that would mean that we're going to have fewer remaining volts over top of this circuit back over here, which means that I'm going to go and actually see that as being a decrease in my value of voltage. It's going to be a dropping value of voltage. This is really good for us because now we can go and take this small weak signal, milliamps or microamps, that's all that we can place through these. We can take that small weak signal, we can see that that voltage has dropped away a little bit, and this is then going to be able to go and respond, and it is going to be able to go and give us a corresponding drop on the output. But this corresponding drop on the output is going to be a much stronger one, where we are going to be able to go and get, actual amps of current that we are going to go and drive out. We could never drive actual amps out of our weak signal like the RTD. We would always be limited to, these milli or microamps. So anytime that we need to drive out more strong current, maybe a proportional valve or something like that you're adjusting to adjust, the flow of glycol in a system or anything like that, you would need to go and use one of these op amps that's going to be able to deliver those actual amps through here. Read on the inside over here as a voltage, deliver those out over there. This situation that we're using it in, we are using what we refer to as feedback off of it. And feedback is where what I have on my output is going to be fed back into one of my input sides over here. And so we're always going to be working to build this thing into balance, because as this voltage over here goes up, then it is going to go up in relationship to whatever this V out was. We'll start with this V out at 0. If this voltage goes up, that means that this voltage over here, because this was at a value of 0 over here, tracing it through, would also be seen as being a more positive. Therefore, this would start to go and rise up as well. And this is going to go and rise up until it matches, till it brings this to a value of 0. Once it brings this to a value of 0, it's not going to increase the amount of rise that we would have on the output. Right now, they're showing us a sine wave coming in here, but in what's an easier way to look at these would be to look at this thing as if I've got a sloped line that then tapers out. What I can do is I could say that right now, here's my value, it's rising. As my value rises, this one over here on my output would be doing the same thing. It's going to start to rise, but it's always going to be a little bit behind, because what it's doing is it is measuring, sending a feedback, and then saying, okay, is this still larger? Yeah, it's still larger. Then I'm going to go and increase a little bit more, increase a little bit more. Now, it happens really rapidly over top of, just milliseconds that this is all going to happen. But there's always going to be a little bit of a lag that is going to be on our output, and eventually when this stabilizes on my input side, this will stabilize on my output side, because it'll have brought it up to a value where it no longer needs to increase it to keep these things together. It tries to balance that out. We can then just use that high current output that we have over here to go and drive other loads, current output to vary a heater. Maybe it's going to be a 0 to 10 volt signal or a 4 to 20 milliamp signal or something like that. The next one that we have is going to be an inverting amplifier. Now, an amplifier is going to go and give us an increase in range. This over here might be a small signal where I'm talking about millivolts. This over here is going to be the same signal, but it's now going to be into full volts that I'm going to go and have fed out of it. The previous one that we looked at, the voltage follower, kept the same values of voltage. It just increased the amount of current. I should just mark that onto here. Voltage, same. Current increased. It only amplifies my current that I'm going to go and have out on the voltage follower. And it does that by passing it in from those outside arms. This one over here, we now have got two resistors inside of it, RF and RN, which are going to go and form a voltage divider. And that voltage divider is then going to be able to give us an amplification that we would need to go and have on our applied side. Because what we'll have is we are going to go and have a voltage drop, RF, over here, over top of my RN that we are going to go and feed out over here. How does this thing work? Well, once again, if I were to start a signal at a value of 0, so I'm just going to erase theirs on both ends, and we're just going to build our own up top over here. If I were to start a signal at 0 volts, so this is going to be at 0 volts, it's attached to ground. I'm going to draw that little arm here, that little arm here. So I can go a little bit positive, go a little bit negative if I need to. What I'm going to go and have is I've got a signal that starts out at 0 and starts to go and climb, okay? As I take that signal and I start to go and climb, inside of here, we're going to go and see, here's that signal that we are feeding in. It's coming in onto this input over here. As that voltage goes up, I'm going to go and drop some of that voltage over top of my input resistor, but the rest of that voltage is then going to go and appear across this little, input over here from my inverting to my non-inverting, where it's going to go and get red, and as it gets red, it is then going to go and cause a change to go and happen. Now, because we're coming in on the inverting, it is going to go and drive this end down. So it's going to start to switch out to this, where I'm now going to go and see on my output side, it's going to start dropping like that, my value of voltage. As it starts dropping my value of voltage over there, what happens is that this resistor, this feedback resistor over here, is going to start to drop in its, or it's going to start to drop volts, but it's going to move into the negative region. Because over here we had a positive, now we're taking this one and we're starting to go and pull this one away in the opposite direction, because what we're trying to do is we're trying to bring this back down to 0. Let me go and demonstrate what that actually goes and looks like. Right now, when we started out, we had 2 resistors. I take a look at Rin. Rin was attached to my 0 volts. We can say that this is going to be 0 volts, and we see that off of here. This would be at 0 volts if this thing was in balance and there was no voltage being fed in. My RF is going to be referencing across from the output, which is also at 0 volts, across to this over here as well. So I can almost view RF as if it were attached like that across my 0 volt to my 0 volt plane that I'm going to go and have over there. Because this arm over here stays at 0 volts, this inverting amplifier wants to go and stay at 0 volts, but we've got these 2 components that are placed together in series like that. We've got that series loop inside of there. So as I start to bring this more positive, what it starts to do is I'm going to go and increase the value of voltage that I'm going to go and see across here. That increase in the value of voltage is then going to go and cause this to go and drop away. And so really what happens is my resistances, I can take that one there, I can pull that one away, my resistances have to get re-pulled across. One of these is going to be attached to my output. That's going to be the far end of RF over here. That's my output over there. This one over here is my V in that I have up top over here. This common point over here, what the op amp is going to do is it is going to go and continue to drive negative values of voltage out, because it is trying to pull this down until eventually I get to this point where I'm going to go and have that common point back to that value of 0, because that's what it's trying to do. It's trying to balance to this one over here. The important thing to note is that this RF is really going to go and control a lot of how far we're going to drive that voltage down. The bigger the value of RF that we are going to go and have, that would mean the larger the resistance that I would see in this section over here. That would mean the greater the value of voltage that I would have to go and drive out here on my inverting lead in order to go and drive that out. So this is just kind of our operation, explained in an easier to follow manner than going through all the, you can go through calculus and you can use summing and things like that to go and cover them. But ultimately what we're looking at is we're looking at a series value of resistances, where those series values of resistances are going to go and change. My in is always going to be on my positive, my out is going to be on my negative, and as I increase my value of in, I'm going to go and increase a proportional amount on my out. I'm going to have to drive and pull this output value down further in order to bring it back to wherever my 0 plane is going to go and be. We've got a formula that describes all of this. I'll just erase a bunch of this. That formula that describes it is going to be my amplification closed loop, or my ACL that we are going to have. We talked about AOL, which is the amplification open loop before. This is now going to be ACL. A subscript C subscript L amplification closed loop is going to be this value of my RF over top of my Rin. The F stands for feedback on this one, my feedback value of resistor. The ratio of my feedback over top of my input resistor is going to determine how far we are going to go and drive that amplification closed loop in the opposite direction. All that I need to do to go and figure out what my output voltage is I have to remember that I'm feeding it in on my inverting input, so it's going to be a negative value, and I take that input value of voltage, whatever it instantaneously is, and I multiply it by this and by a negative, which will give me my output. It looks like this over here. It's inside of your books there. My amplification closed loop is going to go and be this formula right down here. That is going to be my output voltage is going to be negative volts in multiplied by RF over Rn. We do want to have that negative because then we are going to go and catch the fact that this thing is going to be inverted over here. In other words, if I stick in a negative value of volts, negative 2 volts, that negative and this negative over here would cancel each other out, which would tell me that I'm going to go and have a positive out, and that just makes sense for an inverted value of voltage, etc. They give you an example inside of there. They say, hey, look, if I've got an input voltage that is half a volt peak to peak, and I've got an input resistor of 1 k ohm and a feedback of 5.6, what is my output voltage going to go and be? Well, we would just go and take my 5.6 over top of my 1.0. That's my input. That's my feedback over there. That's going to go and give me a amplification closed loop of 5.6. And all I need to do is take that amplification closed loop, that's these ones over here, multiply it by my input voltage. I get half a volt that I am going to go and have on there, 0.5 volts peak to peak. Now note that they did not give this thing any sort of a polarity off of it. It's a peak to peak voltage, which means that it is going above and below. In there, it's just a small waveform. What we're going to do is we're going to take that 0.5 peak to peak, we're going to multiply it by my 5.6, and when I do so, that is going to go and tell me that my output waveform is now going to become a 2.8 volts peak to peak. Oops, sorry, that one's backwards. Because it is inverted, it is going to go and be 2.8, but it is going to go and have its positive and its negative flipped around. All right, here's my out. Here is my in that I'm going to go and have over here. Peak to peak values just tell us how big the output waveform would be. If I had an actual DC value, I could use these same values here. Let's say I got the 5.6 and my input, but if I gave myself a DC value for this, let's say a plus 2 volts, that plus 2 volts would go and get multiplied by this 5.6, and it would have that negative, so we would go and multiply it and then invert it, which would get us to, let me just pull that up there, 5.6 times 2 is going to go and get me 11.2, but it's going to be inverted, so my output for this 2 volts in would be a negative 11.2 volts. Once again, the amount that it's going to go to is still going to go and be governed by whatever I've actually got. We talked about how what it dreams of being able to do is going to be different than what it absolutely can go and do. So if I needed to go and get 11 volts out on this thing, I would need to have at least a minus 12 volts and a positive 12 volts over here, because otherwise if I was trying to do an 11 volts output, it would clip, or I would lose part of that waveform. My output waveform would get clipped off at whatever the maximum value of voltage would go and be for that. Okay, the next one that we're going to go and talk about is going to be my non-inverting input. My non-inverting input is going to go and have a similar layout. We're going to have RF over top of Rin, but now we're going to go and ground that section over here. So we're going to go and attach this down to a value of 0 volts, and then I'm going to go and have these two that are going to be connected in series across to my output over here. This that is going to go and be my input that I'm going to go and take in values of voltage. We are going to go and get a different ACL out of this one. My amplification closed loop, ACL, is going to be equal to my RF over top of Rin plus 1, plus 1 is going to become what this is going to be. And it is going to go and have a differing size to that. Hold on, I just moved my screen. Let's just move that thing back up over here. All right, problems are fixed over there. Move the screen around. Yeah, stuff just went crazy here for a second. But we're back to where we were before, which is taking a look at my amplification closed loop, which is going to be RF over top of Rin. Once again, inside of here, we have to remember that we have got a small voltmeter that is being used to go and measure. It doesn't actually have a small voltmeter, we know that, but we are going to go and then drive from my positive value of voltage, or we are going to go and drive from my negative value of voltage to this output over here in order to go and balance that system. If we take a look at this, we see that my input value of voltage over here, that this is attached to ground over here, and then it's attached to this common point, that my feedback is then attached to my output. And then it's going to be tied out there as well. And what we need to do is we need to go and balance these. So I'm going to go and start by just drawing out a signal over here, or I'm going to draw out a 0 volts line. We know that the 0 volts line has got attached to it my Rin. And currently, right now, my Rin is going to be at 0 volts. We've got nothing tied to it, which means that this point over here on that blue point would be basically as if it were hunched over here. And then at this point over here, this is going to be my feedback resistor. It's as if that thing was hunched out as well, because this is also going to be at 0 volts. We've got nothing to go and amplify. As soon as we take in a value of voltage, let's go and give this thing a positive 1 volt into here. That positive 1 volt over there is then going to go and create a voltage differential. We're going to go and see that voltage differential across there, which this is then going to say in reference to 0, this thing is higher, therefore it is going to start to increase the amount of feedback voltage. So this line over here is then going to go and start moving up. So we'll see that line starting to go and move up. As that line goes and moves up, we are also going to go and start to adjust this one over here, because I do have voltage over here. That voltage is going to go and create current that is going to travel through here. So both of these are going to go and have current through. V is equal to I times R. V is equal to I times R, because there is current that is going to travel through those. The voltage across both of those is going to go and increase. So the top side of this feedback becomes unanchored, same with the bottom side of the other one. And really what we end up having is we end up having both of these now that start to go and float up above here. Top one's being my feedback, bottom one is going to be my input value of resistance. What we'll see is we are going to go and continue to raise this point over here, this top, until eventually it becomes level with whatever my input value of voltage is going to go and be. And it's always going to end up with about this plus 1 volt differential that we are going to go and have off of there, just because we've got some internal drops across my actual components inside of there. Remember, it's all made up of tiny transistors that are all combined together to create this massive, massive op amp. My output value of voltage is always going to go and give this plus 1 plus whatever I have amplified this all the way out to become, giving us this formula that we have over here. Let's put some numbers in and see how this thing goes and responds. In the previous example, where we had the amplification that was going to be our non-inverting amplification, we said, look, what happens when we go and take in a value of 2 volts, and we took it in over top of a feedback at 5.6 over top of an input of 1.0 that we had. And we fed that into our previous one. It wasn't one that was on the book. It's the one where we just kind of made it up, because instead of using the peak-to-peak values, it just made more sense for us to go and use something that was not peak-to-peak off of it. Just so we could see the inversion. Now we're going to take that same 2 volts, we're going to feed it in here, we're going to use these values of K ohms and K ohms over here, and then we are going to go and figure out our ACL. So my output, V out, is going to become my V in, 2 volts multiplied by 5.6 over 1 plus 1. So this value is all going to become 6.6, like that. 5.6 over 1 is 5.6, plus 1 is going to bring us up to 6.6, so we're going to do 2 times 6.6. Gets us out to a value of 13.2. So our 2 volts DC that we were going to go and feed in would come out to become a value of 13.2 volts that I would have on my output, and it would be a positive in the same direction. There will always be what we refer to as this offset, this plus 1 that we are going to go and have off of there, and it's just part of how the actual guts of these op amps themselves go and work. You can't create them without having that DC offset inside of them, so it's just something that you have to be aware of, that when we are doing a non-inverting amplification, that we are going to see those on there. They give you an example inside of the book there as well, where they go through ones that are going to go and be peak to peak, because it's quite common that we are going to go and have AC signals that we're going to go and amplify. If we do have that AC signal, we need to go and have a dual-ended type of op-amp where we got both the positive and the negative. And they say, look, if we're going to feed in 1 volt peak to peak, and if my input is going to be 1 k ohm, and if my feedback is going to be 3.3 k ohms, what is my output voltage going to go and be? Let's combine it all into a single formula. V out is going to be equal to my V in multiplied by RF over top of R in plus 1. So we'll take all those values. We're going to go and put them all in. My voltage input is 1 volt peak to peak, so we'll put that in there. My feedback is 3.3. My input is 1.0. So we are going to be able to take this 3.3 over 1, and it becomes 4.3 by the time we add in this plus 1 over here. Multiply that by my value of 1, and we see that my output value of voltage for a 1 volt in is going to go and be a 4.3 volt peak to peak out. The important thing to note about it as well is that this is only going to amplify the physical magnitude. It is not going to go and change the timing of what we have it. So in other words, what I had on the input side, this is what the waveform looked like. It was just a tiny little waveform, peak to peak. Ah, come on. I don't know why it's disappearing on me here. We'll try that again. It's just a tiny, tiny little waveform that we had coming in, but we were able to get a much larger value out. But where it crosses the x-axis, the frequency of my input is going to go and stay the same. It does nothing to frequency. It only amplifies our value of voltage. That's our formulas. We just went through that. I'm going to move past that one. We're going to move on to the next one, which is going to become my summing amplifier. And a summing amplifier is going to allow me to take multiple voltages in, and then I'm going to go and be able to get a single output value out. It does lead to the question, where are we going to go and use this? Well, there's going to be a bunch of places where we could go and use it, where I'm going to go and look at those 3 situations that they show you down below that are going to go and be I, double I, triple I, and quadruple I, or 4 different situations over there where we can go and change our values of our input resistances, and we're going to go and get different things that are going to go and happen. If I make all my resistors equal, so that's going to be the number I in the underneath the illustration here. If all my feedback and all of my inputs are going to be equal, I see that first of all I'm coming in on the inverting. And on my inverting, my ACL is going to be RF over top of Rin that I'm going to go and have. So I'm going to go and have this voltage over top of this voltage, this resistor over top of this resistor. It's going to be a 1-to-1 ratio. If I make them all the same, what I'm going to get is all of my volts that I take in are going to go and sum together and form my output. So if I had to give myself 1 volt, 2 volts, and 3 volts, provided that I've got a high enough positive and high enough negative supply. We'll take this to minus 24 volts, and this one here to positive 24 volts. I'm going to be able to go and get an output of all 3 of those values of voltage together onto my output over here, which would become out a value of negative 6 volts because it is inverting, and if these are all positive, they do have to go and invert. It's useful for if I have got just 3 different values that I'm reading from something and I need to know the sum, particularly if you're looking at doing something like weighting, right? If we have got, this might be attached to a scale, this might be attached to a scale, our voltage outputs are always going to go and be, our outputs are always going to be in a voltage. This is that whole Wheatstone bridge thing you covered in 1st or 2nd year. You could go and have ingredients that you're looking to go and have. This thing here might be ingredient 1 for whatever you're making. This is ingredient 2, and this one over here is going to be your ingredient 3. Add all 3 of those together, and it's going to go give you, your total that you are going to go and have over here. It's going to be inverted, but you can just re-invert that with a voltage follower if you really wanted to, or with a 1-to-1 inverter. That's going to be my first one that I would go and use. The next one is going to be my inverted percentage sum, where what I'm going to go and do is I'm going to go and have these 3 that are all going to be the same values, and then where I'm going to go and have my feedback that is just going to be a multiple of whatever these these other values are. Whatever this value is, this might be 2 times that. In that case, what I'm going to get on the output would be a 2 times value. So if we say that this is a 1K for each of these, and if we said that this is a 2K for this one over here, and I went with the same values, +1, +2, +3, I would go and get out a sum of these that would be multiplied by whatever the multiplication is from my feedback to my input. In this case, it's going to be 2 times multiplication. So this would now switch out to become negative 12 volts that I would have on the output. Once again, you're going to use this where you've taken a bunch of different measurements and you are going to go and sum them all together to get a final output of it, but you just need to have a larger value to go and drive whatever it is that you need on the output, because we are driving stuff through those legs over there. Number 3, they don't give us any sort of a example for what they are. They just say that for the number 3 that we can go and adjust the individual by adjusting each signal, R1, R2, and R3. Excuse me. Where we might go and use this is if I have got a building. Let's go like this over here. We've got a very large building. Part of that building is going to be shipping. Part of that building is going to go and be manufacturing. And part of that building is going to go and be office. Okay, and let's say that we've only got a single rooftop unit for that. What we're going to go and have is inside of each of these things, we're going to go and have a temperature probe here, and a temperature probe here. Those temperature probes are just going to be RTDs. Now, what I don't want to do is I don't want to go and do all of my building's heat based upon what's inside of shipping. I still need to make sure it's decent inside of shipping, but it's not going to have to go and run the whole building because they're going to have those big doors open and closed all the time. So during the summer, we're going to let lots of heat in. During the winter, we're going to let lots of cold in inside of there. From shipping to manufacturing, we're going to go and have bigger temperature differentials once again in manufacturing as well, because they still have to have their own large roll-up door between them and the shipping department. But then my office, that's where the boss is. That's where we are going to go and have, the temperature that we're going to go and have most regulated. So what we'll do is we'll take each of these temperatures over here. Temperature, we'll call this one temperature 3, this one temperature 2, and this one temperature number 1. And I'm going to go and feed them into here, 1, 2, and 3, those values of voltage that I'm getting from there. And then I'm going to weight them differently. By adjusting the amount of resistance that I'm going to go and have across each one of these here, I'm going to be able to go and adjust the amount of weight that is given to the signal. So I can say that, I need to monitor what's happening in shipping, but I'm going to go and adjust it so that it doesn't have a huge effect on what's happening over here. Whereas what I've got for my office, I'm going to go and adjust that resistance input so that it's going to go and have a fairly large effect, because the office is, where the boss is, and that's where we're going to have to try and keep things most comfortable. Allows you, in this case, we're describing a building with only a single rooftop unit, but if you've got other things where you're monitoring a couple different things, but there's weightings that apply to them, this is where you can go and use that input, where we change different values of resistance for each one. Last one that we have is where we are going to go and take the signals and we're going to go and average it. Once again, really, really handy for doing averaging. We could go back to that same idea of a building, but now it's, all 3 of these temperature sensors are inside of the same loading bay, let's say, and inside of that loading bay, I'm then going to go and take an average of it. It's going to be colder, closer to the door. It's going to be warmer, closer towards the back wall, but I want to go and average it. So what I need to do is I need to go and make sure that these are each going to go and be tripled, so they're going to go and average out. I would give this thing a value of, let's say, 1K, and each of these would be 3K. And then what I would be able to do, we'll go back to those values of volts, 1 volts, 2 volts, it's a 2, I don't know what I'm doing here, and 3 volts over here. What's going to happen is with each of these being 3Ks here, we're going to get a smaller weighting out onto here, and what I'm going to get out of this is going to become a negative 2 volts. It's still inverting that it's driving out, but it's going to be inverted average of those 3 volts that we will have over there. This makes it really, really handy for us in a lot of industrial applications. You'll note that the bulk of the industrial applications that I'm talking about have something to do with temperature. We use these things for feedback on temperature. We can use them for position as well, but we've got better things that are going to give us, feedbacks on position. The bulk of where these things are going to go and be is going to be on monitoring for temperature or monitoring for current in a lot of cases as well, because we can go and take, CT values off of other stuff and we can feed that back as voltages onto other things. So yeah, really handy inside of industrial applications. Some of you will never touch one in your entire career. Others of you are going to, go quite a ways into it, depending upon the type of work that you do and how involved you get in the work, whether you're just going to be the power electrician on site or whether you're going to handle the instrumentation, etc. Next one that we're going to talk about over here is going to be my op-amp integrator. They are going to go and be a specialized circuit. We're going to go and have the integrator and the differentiator that are going to go and be there. And they do say make sure you don't confuse the differential with the differentiator that we are going to go and have. But it's not going to make much of a change to you guys. Really what we are going to have from the integrator and the differentiator is we're going to go and get specialized outputs that we can go and run out of here, where we can either go and take mathematical averages or we can figure out slopes of a line. There's this thing inside of controls called PID, proportional, integral, and differential. That is going to go and be basically like saying, the history of where something is, what we still need to expect for it, and what we currently are doing is 3 ways that we go and look at how we adjust the speed on something like a motor. Proportional, integral, and derivative, we combine all 3 of those, where we currently are, where we were before, and how far we have got left to go is the short form for these. Then we can go and figure out exactly how fast we should be running a motor, etc. It's like having your eyes and your feet and your reflexes in your own car. When you're coming up towards a stoplight, you do not just come roaring up and then jam the brakes on at the last second. It's hard on your vehicle. Same as when the light says go, you don't just hammer down and peel out across that intersection. If you value your vehicle and you're not showing off or anything with it, what you're going to do is you're going to go and ease into it. You're going to go and ease out of it because you are watching. You see what speed you're at. You see how far you've got until you hit the light, all of that type of stuff. So you slow this thing down so it's nice and gentle. We'll do that inside of all of our industrial through what we are going to go and refer to as PID controls. Sometimes we'll just do PI as well. And then those are going to go and get signals that are going to be the integral and the differential. We can get both of those out of op-amp integrators and op-amp differentiators that we are going to go and have. They don't even show the differentiators, but they're going to go and give us rate of change that we are going to be able to get out of this. And really it's just because of the lagging effect of a capacitor over here. You can use this thing to either go and take out your integral for a PID system, or you can use it for what they talk about, that we can get a triangular shaped wave from a digital input signal, a signal that is going to be going in and out as a square wave. What we are going to be able to do is we are going to be able to go and change that slope into there based upon what my components are going to be, the size of the capacitor and the resistor over there. What I'll be able to do is I'll be able to go and change what that slope is where it starts out. So I can either go hard in and then hit a peak, or I can go slow in and maybe I will never even hit the peak itself. Don't worry too much about these because they are a complete, electronics type of thing. You're not going to go and design a lot of these. You're going to take, as an industrial electrician, you will take PI and PID and you will apply that inside of your variable frequency drives, but you probably will never design one of these circuits. Just recognize it for what it actually is. Okay, let's talk about the DAC, the digital to analog converter over here. DAC is going to go and be anything that converts digital signals, highs and lows, into analog signals, which are going to be, anywhere between my range of voltage from 0 to whatever the maximum voltage is going to go and be. And they work off of our summing amplifier. What they're doing over here is they're showing us a digital input off of here that is going to go and have weighted signal. So if I were to take a look at this, I see I'm coming into my inverting. I see I've got a feedback and an input resistor. And I'm just going to take a look at each of these channels individually. Just real quick over here. I see that that first channel is going to go and have an amplification of RF over top of RIN. That is going to be 8 over top of 5. right? That's RF over RN. So I'm just going to go 8 divided by 5 gives me an amplification of 1.6 that we will have out of it. So the first channel here is just going to be a 1.6 channel. I'm going to put that just over here. The next channel, using the same RF and RN that we are going to go and have, is now going to be an 8 over 10. 8 over 10 is going to become a 0.8 that we would have. The next one down is going to go and be 8 over top of 20 that we would go and have for that. So it's going to become a 0.4 if you do the math. Oh, that's not my red marker. 0.4. And then the last one over here is going to become 8 over top of 40 for that one, which is going to go and become a 0.2 for my amplification. Taking a look at these 4 numbers, you should notice that there is a pattern that we are going to go and have over here. That pattern that you're seeing is what we would refer to as a binary pattern, where it's going to be doubling from one to the next, one to the next, one to the next. We're going to learn about binary numbering systems under level 3 and sometimes level 4, depends on whether you're in harmonized or non-harmonized. But binary number systems, every positional weight is going to go and double. And we see that off of here. My amplification, 0.2 doubles to 0.4, 0.4 to 0.8, 0.8 doubles to become 0.6 over here. So we're going to go and give different weightings to each one of these. If we go and take in a value of 5 volts on every single one of these, each of them is going to go and give us a differing value that we would go and get out of it. If I were to take 5 volts in onto this, 5 times 0.2, or 20% of 5, is going to go and give me a value of 1 volt that I would have from that. 5 times 0.4 would give me a value of 2 volts that I would have from that. 5 multiplied by 0.8 for my amplification is going to go and give me a value of 4 volts that I'm going to go and have for that. 5 multiplied by 1.6 is obviously going to have to go higher than that. It's going to go and take me to a value of 8 volts that I would go and have for that, my amplification closed loop. And so if I had highs on all of these, highs being that it's going to be 5 volts, this is a discrete or a binary system. If this is 5 volts, that is going to go and be high. If this is 0 volts, that's going to go and be a low. I would see that I would have a value of 8 volts plus 4 volts plus 2 volts plus 1 volt. And if I would take them and add them all together, 1 plus 2 gets me to 3, plus another 4 gets me to 7, plus another 8. That would tell me that I'm going to go and get to a 15 volt output that I would go and have here. That 15 volts is going to get driven from the source. It is inverted, so it is going to come out as a negative 15 if these were all positive values of volts that we would have over here. But I would go and get a 15 volts out. Now, you have not covered binary numbering systems yet, which is a pity, because if you did cover binary numbering systems, you would know that 1111 is going to be the binary number 15. That's going to be a high is how we would also be able to say it, is going to be a binary number 15. And over here we see that we've got a binary that is going to be high as well. What happens if one of these changes to a value of 0? Well, let's go and try that. Let's change these two. We'll put these two in as being values of 0 right now. 0 times 0.4 is going to be a value of 0. 0 times 0.8 is going to be a value of 0 as well. So I would have a high, 5 volts, low, 0 volts, low, 0 volts, high, 5 volts over here. And I would get out of this high 1 volt, and out of this high 8 volts over here. If I add them together, that would go and give me a value of 9 volts that I would go and have out of here. Negative 9 because it's inverting here once again. This would translate into my binary number 9 that I would go and have over here as well. So where these are really, really useful is I can go and take binary numbers and I can convert those binary numbers into something that is going to go and become an analog output. We need to do this in a lot of our control types of systems over here. They do go and give you, a few more examples. You can take a look at those on the next couple of pages. And they tell us as well that, hey, look, if these values of volts over here, if this 5 volts was not a true 5 volts, let's say this thing was at 4.8 volts because there was some drop in the system, I would not get out an 8-volt system for that, I would have something different. We'll just try this here. 1.6 times 4.8 gets me to a value of 7.68. So rather than getting the true 8 volts out that I should be getting, I'd be getting 7.68 volts out. So it would be introduce what we refer to as error inside of these. So what we'll do is we can then go to a precision value. Over here, we're going to have the exact same system, but where we are going to go and run that system through another set of op amps that are then going to go and be run in a way that is going to go and just allow us to drive these things rail to rail. We're going to go and have, if we've got a high value, we're going to go and use amplification open loop, AOL, off of these ones here, and they're not showing the second line of these. The second line of these is just going to be tied down to ground for all of these over here. But anytime that I go and take any one of these and I put in a value, 4 volts, 5 volts, anything in that range, what it's going to do is it's going to go and drive that thing hard into open loop amplification, and then it's just going to pass this precision 5 volts through. So that we've got a 5 volts over here. From here on down, it's the exact same circuit as this one that we were looking at, our figure 6. All we're doing is we're just putting in those precision modules and using other op amps ahead of it to go and drive us out to a proper full 5 volts. That way we can take janky signals in from other stuff that's going to be out in the field that might not be going all the way up. The high in the field might be a value ranging all the way from 3 to 6 volts, and my low might be something that's going to be smaller inside of there. So what I can do is I can take that 3 to 6 volts anytime I'm in that range, provided that I set these ones up right. It's going to read that properly as a high and provide that full 5 volts that we would need off of it. Well, we can go digital to analog with these things. We can also go analog to digital with these. And an ADC is going to be the opposite of my DAC. The ADC is just going to go and take in analog values of voltage. It's going to compare them, and then it is going to go and give me digital outputs from these ones. Now, what it is not going to do for me off of this is it is not going to go and give me a binary value out of there. What we're looking at over here is we are looking at just a set of lights that are going to go and light up, ding, 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 as we go across here, based upon whatever my analog value of voltage is. You see these things all the time in industrial things where you have like a level sensor. You might have a tank that's a sealed tank. You can't see what's inside there, but on the side you're going to have one of those little LED bar graphs that is going to go and kind of show you roughly what the level is. And they're doing that through an analog to digital conversion. You're going to go and have analog feed in coming from your weigh scales, and it is just going to get compared against some other values of voltage to go and give you these outputs on the side. Here's how it works. Once again, all we are going to do is we are going to go and have a reference value of voltage. What I want you to see is I want you to take a look at this blue run over here. What you see is that we have got 5 resistors that are in series. Each of those 5 resistors has got an equal value of resistance. This is important to note that we've got equal values of resistance, because that means if each one has got an equal value of resistance, then we are going to go and split up our voltage equally by the number of resistors over here. You can Ohm's law, add these all together, get 50k ohms, use 5 volts, figure out your current, etc. across here. But if you are comfortable enough with voltage divisors, and that's what this thing is, we would see that we'll divide 5 volts, which is what my input is, up into 1 volt sections. So from here to here is going to be 1 volt. From here to here is 1 volt. This is another 1 volt, this is another 1 volt, this is another 1 volt, and sorry, that one over there is 1 volt as well. What we then do is we just tap off of this thing and we put it in as a reference. So this section over here is at the 1 volt. This one is 2 resistors up, it's at 2 volts. This one is 3 resistors up, it's at 3 volts. This one is 4 resistors up, it's going to be at 4 volts that I'm going to go and have over there. And then we just go and compare everything inside of here. So we're going to feed in an input value of voltage. Let's start with a 3.5 volts that I'm going to go and feed into here. What we're going to do is we are going to go and compare that 3.5 volts inside of here. We're going to compare the 3.5 volts to my 1 volt that I have on the system. And we do have to say which of my inputs am I coming into. If you take a look at that, you see that you're coming into the inverting input. The inverting input means that this thing is now going to go and switch out to a negative, or to the most negative point it can find in the circuit, which is going to be this ground that we're going to have over here. So let's compare our values of voltage. Right now we see this 3.5 gets fed to each of these. So over here I have got 3.5 compared to 1 volts. So when I compare these two, what am I going to see? I'm going to see that 3.5 is a positive 2.5 more. It is plus 2.5 when I do this comparison of those two values. If it is a positive value of voltage coming into an inverting, that means that the positive is going to go and get driven out to become a negative, right? Positives change to negatives through this inverting, which means that this thing is going to go and switch hard towards the ground. Note that there's no feedback. There's no amplification. We are operating these things in AOL, which is amplification open loop, which means that they're going to drive hard in either direction. So because this has got a positive value of voltage and it is inverted, it is going to drive it to ground. And if I go and follow that through, I see that I've got a ground and a 5 volt. Do I have a complete path for current flow? Absolutely. I've got a complete path for current flow going through here, which means that that light is going to go and light up. Beautiful. We got an LED in here. It's properly biased. Anode to the top over here. The 330 ohm resistor in there is just a dropping resistor on my LED. That's my first one. We'll go up to the next one. Same deal. We're just going to go and compare these. Now we are going to go and have 3.5 compared to my 2 volts. That's going to be my reference over there. And I see that I'm going to be plus 1.5. So I'm going to be a positive value. That positive inverts and becomes a negative. This one is also going to go and ground down. So now we've got 2 of these that are going to be grounded down. Each of these means that my light is going to go on. We'll go up to the third one over here. We're going to compare our 3.5, our input, to our reference voltage, which is going to be 3 volts. And I see that I'm going to go and be a value of 0.5, but it's a plus 0.5, and my amplification open loop is going to be sitting around 200,000. So it is still going to go and drive hard into my negative over here, which means that switch to the negative, and this is now going to be turned on. Last one over here is going to be my 3.5 that we are then going to go and compare to my 4 volts. So 3.5 compared to 4 volts. What's the difference? Well, it is a negative 0.5 difference. It's smaller than its reference value over here. So I'm going to feed a negative into a negative, or into an inverting, which means it is going to go and amplify that, but it's going to switch out to the positive. So it's going to switch over here. Tell me, what is the potential difference between this 5 volt and this 5 volt? Well, if you take a look at it, you see there's no potential difference. If there's no potential difference, is there going to be any current flow? Absolutely not. So this LED over here is going to be off for these ones. What we have over here is we have got just a very, low scale over here that's telling us, basically a volt at a time what we have got on our system itself. It's got a relatively poor ability to tell exactly where we are. We were at 3.5 volts. If we wanted to go and increase how much we could tell, what we would have to do is we'd have to add in more op amps, and we would have to go and increase the number of sections inside of my voltage divisor. This is going to be referred to as increasing the resolution, or how fine of a component that we can go and look at inside of these. You use that term resolution all the time for stuff like televisions and computer screens, etc. It's the same thing for resolution of a measurement. It's just going to be how fine we can drill down. If I would double the number of voltage dividers inside of here, or the number of resistors inside here, I would be able to take this down to a 0.5 volt. If I would go and double that again, I'd be able to go down to a 1/4 volt resolution, etc. across here. Okay, that is a lot to cover through on your op amps, but we are through with those at this point. On to the next.